Okay, so let's do a bit more topology. So this is the way we progress, or might progress from metric spaces, and that is the looking at different ways for sequences to converge, as well as what if they're the same. Okay, so so this was search for a metric that would give us a pointwise convergence of functions, that there is no such thing. Okay, but then on the other hand, you can ask yourself, what if you change the metric? Does it mean that the convergence also changes? And the answer is no, once again. So it's actually fairly easy to see that. Look at it. If you look at the definition of convergence of sequences in a metric space, which is here, does it matter if I look at it? This is my definition. Okay, the distance appears only once. I take that and I multiply by 2. So I take the whole metric space and create a new one with the metric equal to twice the old one. Okay, so once again, like switching from miles to kilometers, and the answer, and then ask of what does it do to convergence of sequences, and the answer is nothing, right? If you look at this definition, so whether I have D there or I have 2D, it won't matter. I'll have just to look at slightly more steps into the future with n. Okay, so epsilon, if epsilon is the same, may have to make more steps into the future, but the match is clear. So I have twice dxn x less than epsilon. Okay, it's the same as dxn x less than epsilon over 2. Okay, so still applies. If one condition is satisfied, then the other one does too. So metric is not really bound to sequences and their limits as much as it appears. So even though it is defined in terms of distances, the convergence is defined in terms of sequences. It doesn't have to be you can have the same convergence with different matrices. Okay. So and then the surprising results are for example, here these are in fact these will produce the same. That picture in the middle, they will produce the same convergence. So taxicab metric and Euclidean metric have the same convergence sequences. Okay, so that is in other words, the same topology, different metric. And the topology meaning this definition over here, it is nothing but open sets. So the open sets relative to the Euclidean topology, Euclidean metric, or to taxicab metric, the one in the middle, will give you the same open sets. Okay, so it is a surprising result, but it is quite profound. That's why you frequently study topology apart from or beyond metric spaces, because looking for the way we introduce metric spaces is what do those Euclidean spaces that you encounter in calculus, what do they have in common as far as sequences, convergence of functions, or sequences, points concerned, and then what do they have in common, and then metric space, it gives you everything pretty much. But then you can look forward beyond that and ask yourself, what if you have different metric spaces, might they have the same topology? And the answer is once again yes. Okay, so open sets. So how do we make that connection? We look at the open sets in R2 to begin with, and that's how it is defined in the middle. Open set when there is a disk around that point, around every point in that set, if that is does not intersect the complement. Okay, so BXR lies entirely inside of V. Okay. Okay, so that those orange pictures indicate that. So that creates a lot of things that we encounter in calculus. But let's first make sure that that's what I started doing here. Well, in retrospect, maybe let's maybe maybe examine this connection over here a little bit more before proving anything about metric spaces versus topologies. Let's look at the open sets to begin with. This is the definition. Open sets, where do they appear? They don't really appear that frequently in calculus, but other things do. And one is so we'll get back to these theorems, but let's take a look at something more. Yeah. Can I move it? I did. Okay. Okay. So U or whatever V in R2 is open when for every X in V there is positive R such that BXR lies entirely with V. So once again, this is, you have to exclude this in order to be able to fit the circle or disk inside of it necessarily. And so maybe open sets don't appear that often. Well actually, let's make clear that if we take Rn, so n is equal to 1, it is an open. Remember why you say open disk, because that open disk is open. Okay, n equal 2, but n equal 1, it is what is an open. Open sets are intervals. So once again, the term open reappears. So open intervals such as this, and that, and this one. These are open sets, these intervals, and their unions. Okay, so in calculus 1, you encounter open sets. They're just they happen to be this simple. They're just intervals, whether finite or infinite, and so the word open then is applicable. Okay, what is more common is closed. N equal 1, once again, what is closed? We had closed intervals. Remember, so AB, A infinity, B, A negative infinity, B. Okay, so these are closed intervals. Are there closed sets? So once again, I start with open sets. This is it is defined in terms of metric spaces. So we think of R2 as or Rn as a Euclidean space, metric space to begin with. We have the definition of an open set right here. Then we look at all their examples. N equal 1, N equal 2. We see open disks and open intervals in dimension 1. Okay, so let's look at dimension 1. But that, and then remember that we also had open closed intervals, right? So there are open sets and there are open intervals. There are closed intervals. Are there closed sets? What do you think our closed sets are on the line? Oh, okay, can you suggest other closed sets? So we have, let's suppose these are 3 closed sets that we do know are closed. Do we have more? Can you think of more closed sets? The Z, okay, interesting. Z is an integer. Well, then I suppose the how about the simple example? How about a point? A single point. It is a closed set. If you whatever the closeness, we haven't defined closeness yet. But I'm trying to have a few examples so we can try to think of how we should understand closed sets versus open sets. So Z open a point, 2 points, 1 point, 2 points, Z infinitely many points. What about sequences? Say 1, 1/2, 1/3, 1/4. Is the sequence closed? Well, I'm not sure if we have. Well, what do you think? Do you want it closed or not? Does it make sense to call it closed? Well, well, the answer is actually well, the answer is no. It's not closed, and why? Because the way I've written it as a set, it does not contain its limit, and that's what make it not closed. Okay, so that's how traditionally in calculus that's how you describe closed sets. By those that contain all of its, but by those sets that contain all of those of their limits. Okay, so if you have a sequence in a set, so say you have G in real numbers is closed F for every convergent AN in G, limit AN also belongs to G. That's certainly one way to define closed sets. Okay, closed if every convergent sequence also includes the limit. As you can see, it is not typically what you see with open sets. Because you can imagine a sequence like this, and even though the whole sequence lies inside of that's an interval, let's say an interval like this. If this is my interval, okay, then a sequence that behaves like this, 1 over n, will not say 1 over n. Yes, if that sequence will converge to 0, and 0 does not belong to the set. Okay, so, and then we don't call it closed anymore. We don't call it, it's not closed. Okay, so under sequences, we do not jump out of the set. So kind of if you have now those two pictures on the at the top, look at the picture, you can see that these two behaviors are kind of opposite of each other. Open, closed. That's what you expect to see, and the answer is actually quite simple if you look at it topologically. In topological space, a closed set is simply the complement of an open set. Okay, you can think of this as a definition. So I have two definitions, and you can have, as it is frequently in mathematics, you can take one as a definition, and the second one will be a theorem, or the second is a definition, the first is a theorem. Either way, you have to prove it that it is the same thing. So, every convergent sequence, every limit of a convergent sequence remains inside of that set. One point of view, another point of view, it is the complement is open. Okay, so well, it is. Let's try to show it at least one way. So if you just put the definition of convergence next to it, it won't look that bad. So say this is A. So the distance in a metric space A and A is convergent to 0. Okay, so that is the definition of a limit. So so if you think about it, so the limit is a point, so that the sequence, the distance of the element of the sequence will go to 0 as you progress through the sequence, and then on the other hand, the situation is kind of opposite of. So this is A for an open set. Okay, so that's a convergent sequence, and my set then might look like this, set G. Okay, so it might reach its boundary, was still to be defined, but it will not leave the set. Okay, so that's closed. And the distances are getting closer to 0. So on one hand. On the other hand, what if this is not the case? So suppose so this is G and this is, say, D. The complement is V. Okay, so so we don't know what's happening here. That is the exact issue for us to worry about. Does that point A belong to G or does it belong to V? Okay, that is to be decided. And so suppose V is equal to the complement of, let's say, R minus R2, Rn doesn't matter, minus G. Okay. And so the complement, then the complement of G is V, the complement of V of G is V, of G is, of V is G, if G is V. Okay. So, okay, so, so let's see, and now suppose it's open. Okay, going back to the definition. So, and suppose, so then, by definition, where's my definition of open set is right here at the top. So I can separate, once again, I can separate that every point from the complement. So if we're talking about V, I could separate every point in V from G by some R. So like this. By definition, for every x in V, there is an R. I'm just rewriting the definition such that B XR is entirely inside of V. Okay, so in other words, if this is my point and this is my x, it's in V, then I can separate it once again from G. Okay, so VXR intersection with G is empty. That's what this picture is supposed to indicate. So now ask yourself, is it possible that our sequence converges to this x? The sequence lies, so AN is in G. X is in G minus R2 minus G. Okay, so which means that it is open, so it is separated by it is not its distance, if you like, its distance from x to G is positive. Okay, so that's another way to interpret distances in this context, is distances between not just between points but also between the sets. Okay. Or point to a set, and that if you look at this picture, then what we're seeing here is that the distance, what is the distance from x to G, and it appears to be larger than 0. That distance is at least r. Okay, but the point is that it's larger than 0, which means that this condition cannot possibly be satisfied. Okay, so at least that is how we would deal with this, and as that would be an idea of the proof. So the point that all points outside of G, if G is closed, will have to be positive distance away from the set, which means that there cannot be conversions to those sets. Okay, so and that is the proof that well, you can probably do it at home. So finish the proof. Okay, so once again, it doesn't matter what dimension you want to take, dimension 1, 2, or 3, and so on. It will work out just the same way, because ultimately we're talking about metric spaces. So 4 metric spaces. So you don't have to bring in anything like the triangle inequality. That's all been taken care of. But that's the idea of all the limits, all limit points of a set will be contained in that set. So convergence sequence is not closed unless it includes its limit, if there is a limit. Of course, some sequences don't have limits. Then what do you do? There's some slightly more complicated. Okay, so that is why we care. There another thing that you see. I'm trying to remember in calculus 2 closed sets. Under what circumstances closed sets come up in calculus 3? Well, one thing I'm sure you remember. Remember Green's theorem? Anyone?
Is this Cap theory?
Yes. Green, Stokes, Gauss, divergence theorem, any of those? Usually very little time. I have had the same problem. For these theorems, they called frequently the fundamental theorem of vector calculus, and so it only until you deal, and that's where everything comes together. So you study parametric curves, you study say vector fields, okay, and then at the end they come together in one theorem. And then Green's theorem, that is the two-dimensional analog of the fundamental theorem of calculus. Okay, so I don't really want to look at the formulas, but just to refresh your memory about the fundamental theorem of calculus is the integration from, well, you can tell me, what is this equal to? The fundamental theorem of calculus. Calculus 1. How do you evaluate integrals anyway? Definite integral. This is a definite integral. How do you evaluate it? No recollection?
Would it be capital F of B minus capital F of A?
That's right. Okay, and where just to be complete, F is what?
The integral of F.
Yeah, so an integral or antiderivative of F lowercase. So in other words, you do indefinite integration to find F capital, and then you're pretty much done, because then you just plug in two values and subtract, right? So what is, however, what to do when you have functions of higher, or rather you're dealing with high dimensions. So this is dimension 1. So function y equal f of x, and it's antiderivative, both functions of one variable, and that's what you integrate. And then what you're looking at is on the right you integrate over integral AB. Integration over integral AB, and the answer might be the area, right? So as you can see, the integral that is spread, it gives you the area, let's say, spread over integral AB, but that's what's on the left, and what's on the right is only A and B. Turns out that if you carry out the integration correctly, find F capital, then you don't have to worry about that what's happening between A and B. You need only the value of F at A and B. That's it. Okay. So then what is the relation between these two sets? One set AB and the other one points A and B. And the relation is, informally you usually say A and B are the endpoints of the integral AB. So that language is however, it breaks apart once you go to high dimensions, because then your integrals, remember what you integrate, well, what you might be integrating in, say, dimension 2. Okay, so if you're talking about dimension 2, then your integral becomes a volume integral, right? Remember those double integrals? And you integrate over a region on the xy plane, and you're trying to find a volume. So instead of this area that we're trying to find in calculus 1, later on you have a surface. This is y equal f, or rather z is equal to f of xy. Okay, like this. And then you're supposed to find your double integral is the volume, remember? Right? So that double integral, say this region is, say, I don't know, D. Okay, so D is in the plane, and you might be interested in this double integral over D, f of xy, dA, which happens to be the volume under the graph of the function. Okay, so that is the analogy that is I want to not really to pursue, but just point out the issues that you have to face when you want to have a fundamental theorem of calculus for dimensions higher than 1. I mean, unfortunately, there's so much time is spent in dimension 1, calculus 1, then it might seem that the whole calculus is dimension 1. One variable here, one variable there. But you know, in calculus 3, you certainly have felt that there is more going on, and you have motion in dimension 3 or higher, or you have volumes, you have surfaces, you have areas, volumes, surface areas, you have volumes of objects in 3D, you have center of mass, whatever, all of those things have to be treated suddenly in one semester. And so we'll just look at a little bit of that, what you face there, and you certainly would like to have the fundamental theorem of calculus for this new situation, and there is one. So my region in the xy plane is then say something like this, my D. Okay, that's my D, and then there is the right hand side. Just the switch is very similar to this one. So here we had an integral. We had an integral on the left. We had an integral, and it's and then we integrated over the integral on the left, and then we are reduced that integral to an integral over, or not integral, but rather kept referring only to the 2 points A and B on the right. Okay. So similarly, situation happens in dimension 2. So what do you do? What you do is you deal with this. Oop. Stupid. Okay. So you see what I'm doing here? So what's left? the outline. Yeah, there's a word for it. It's called the boundary of D. Okay, so you can see. I hope you can see the analogy between dimension 1 and dimension 2, right? So this is dimension 2, and this is dimension 1, and what I'm saying here is the transition from the interval to its two endpoints is similar to transition from this region to its outline. Okay, the word is the same, topological term that is used in either case is the boundary. Okay, so then it might seem a bit strange, but I hope it is not unnatural to say that the two endpoints of an interval form its boundary. Okay, while a curve that bounds a region is its boundary as well. If you go into dimension 3, you have a solid object. What is its boundary? What bounds a solid object? The surfaces, right? Okay, so that is the hierarchy that you discover in calculus. An interval is bound by 2 points. Okay, a region in the plane is bound by its outline, a curve. Okay, so from two points we go up to curves. Okay, and in dimension 3 a solid is bound by a surface. So that keeps going into as many dimensions as you need. You have from points, curved surfaces, okay, and beyond. And so then I don't want to really do calculus here, but I do want to understand what is the meaning of boundary in the context of a metric space. So can we have one definition that covers all of these 3 cases? So once again, if I really want to do it, I will. It's harder to visualize now if you're talking about a 3-dimensional region. Okay, so I can suggest on what I'm trying to suggest here is that I have a solid here, and I have a surface there. Okay, so this is a region, and this is a curve, usually represented as a parametric curve. In dimension 3, it becomes more complicated because, well, now your solid is bounded by surface. Okay, solid that contains everything inside, but if you throw out what's inside, you end up with a surface. Okay, and that is the relation that the fundamental theorem, such as Green's theorem, is based on this fundamental relation between sets in a Euclidean space. And specifically, it is how we find the boundary of a set. So how do we define boundaries in the metric space environment? Okay, so which means that we have nothing but distances. So define the boundary of, say, A in X, a metric space, using nothing but distances. So intuitively, we know what we're talking about. So once again, this is G and this is V, 2 complementary sets. And what is so special about that kind of line or set that separates them? So what is so special about this point? So V on the right, G is on the left, and some points in between. So how would you explain what you see? What is so special about this pink point? What is so different from pink point from the blue point here and the green point there?
It's on neither.
What?
It's on neither.
Right, but we haven't decided whether we haven't decided whether does it belong to G or it does belongs to V. It can go either way. So G could be closed or V could be closed. But what is so special about that, it is there, the green point is no question, it is not the boundary. In blue point, not the boundary either. What's so different about the pink one? That there is even a question about it. Is it in the boundary or not? What is the boundary? How do you define a boundary? So two objects separated by nothing, and there is some area there right between two hands that are so special. What is so special about those points relative to these two? In terms of distances, what can you say about the distance?
Distance to the boundary?
Distance, no, actually to those two sets. Think about what is the distance of the pink point to these two sets. Well, let's approach it this way. This is X, this is A, and this is B. Okay? Distance from A to G. What do you think it is? 0. Okay. Distance from B to V is, okay. Now, what about distance from A to V? Distance from A to V, what do you think it is? It is what?
Greater than 0.
It is greater than 0, right? You can see the distance, right? Same thing here. Distance from B to G is not 0. It is positive. There is a gap there. Okay. So as you can see, there's nothing special about these points A and B. That's what not so special about it. And now the distance of now going to X. What about X? dx G is 0, and dxv is also 0. So that is the difference. So it is the distance to the other two sets is 0.
So just because it's 0 doesn't mean it belongs to it?
That's right. So we don't want to say about whether it belongs to either of the two sets or not. It might that boundary might belong to this, to that one, or they could share. After all, G and V might actually intersect if that matters. But the point is that it is the distance from the to the other set, to both sets, is 0. So that is truly being between two sets if you are infinitely close to one and the other two. Okay, so if a set belongs to V, then of course it is distance to V will be 0. If it belongs to G, then its distance to G is 0. But then it will be separated from, or might be separated from the other set. But if it is not separated from the other set, then that would be a boundary. More specifically, you don't really have to deal in that manner. But with distances, we didn't really define what the distance to the set is. But we can say that X belongs to the boundary of set G if for any positive R, no matter how small, any the ball BXR intersects G and it intersects the complement. Okay, so that's the definition of the boundary. You cannot separate it from the set itself, nor you can separate it from the complement. It doesn't matter. It could belong to one set to belong to the complement. It doesn't matter because it is It could go either way, but what it makes it in the boundary is indeed that no matter how small the ball you take around that point, it will cross both. Okay, so that confirmed what the picture we have on the left. Okay, so any ball will cross both both of the sets. So I'll have some stuff here to the left, and then I have some stuff to the right, always, no matter how small. So the set from the left reaches all the way to x, and the set from the right also reaches all the way to x. Okay, that's what makes it the boundary. And let's take a look at these three pictures again to confirm that indeed it works out. That if I try to have an interval, we're talking about a ball, so it will be an interval right here around A. No matter how small an interval around A I pick, it will cross both the interval AB and the complement of the interval AB. There will be some half of that interval will be to the left of A and the other half to the right of B, so it will have, in part, no matter how that small interval is, it will satisfy this property. Similarly, here I have literally disks, and the disk one, once again, it will be, even though part of it is on the inside, some of it will be hanging out on the outside, and so that confirms once again the idea that that point belongs to the boundary. That's what it means. In 3D, once again, it's harder to make a picture of, but you can imagine the balls around every point, they have this kind of property. So it will, like, if I try to make a picture here, something like this. Okay, so this is the part that you see is the lies on the outside. So it's like sticking out. Half of that, roughly, of that ball will be on the outside, and the other half will be on the inside. And so then that's how you have a calculus fundamental theorem of calculus for all dimensions, not at once, but at least the topological part of the fundamental theorem is taken care of. So as you can see, integration in the original fundamental theorem, you have integration on the left and no integration on the right. Right? Look at it. Because if you're talking about points, there is no integration there left. If you go to dimension 2, the next line, then you have double integration on the left, and you will have a single integration on the right. Integration along the curve, it is a single integral. Okay? Or in the next line, you have a triple integral on the left, and you have a double integral on the left, on the right. Okay, so there you go. So that is the relation between these different integrations and in different dimensions. The calculus part still remains, but this is the topological part is certainly is more or less taken care of because all of these Euclidean spaces are metric spaces, and so if we have metric spaces, metrics taken care of. So I still don't say what we have over here, what that single integral is equal to, so you have to look up at that in a calculus course. Certainly every calculus book has it. But topologically, it's just a way why we care about open sets, closed sets, boundaries. That's why. Okay, so you can see then now how the boundary comes into play here. An open set does not contain any points of its boundary, while the closed does. The closed set does contain all the points of its boundary. So that's the difference between the two. And well, the standard warning is sets are not like doors, so they don't have to be either open or closed. Some sets are neither. What sets do you know that neither open nor closed? On the line. Well, think about intervals. There are closed intervals, there are open intervals, and what else? There's another type.
Infinite's considered open, right?
It depends. It's a fair question, certainly, but it really has nothing to do with open or closed. In fact, if you look at the list, where's my list over here? They have a similarity here. So infinity is always excluded because it's not a number. So we never include it in our list. So infinite will be, so A infinity, this one is in fact closed, even though it does not contain infinity. Why? Think about it. Take such an interval, A infinity, and consider a convergence sequence. If it converges, then that point has to belong to the interval. If it goes to infinity, it has no limit. So that's why it's closed. So the third type of intervals. I have here 6 different types of intervals. There is one more, just one. Open, closed, and empty. Empty set is empty set open or closed, judging by the definition. Well, look at is it closed? Look at the definition. Is it closed? Every convergence sequence will be, its limit will contain in that set. The set is empty. Okay, use your logic. You have an empty set. So how do you verify that the set is closed? You pick a sequence in it, and then verify some condition, except there are no elements in the set. So you cannot even pick a sequence, which means, is the condition satisfied or not? It is satisfied. Every sequence satisfies the property. There are no sequences, which means every sequence satisfies the property. Right? You can disprove it if you find a sequence that does not satisfy the property. Can you find such a sequence? No, because there are no sequences. Okay, so empty set is closed. Is it open? Yes, it is also open. Okay, so next time.